TensorFlow. TensorFlow is an open-source machine learning framework developed by Google. It is used to build, train, and deploy machine learning models. TensorFlow provides a flexible and efficient platform for creating machine learning models, and it is used by researchers and developers all over the world. In TensorFlow, data is represented as tensors, which are multidimensional arrays with a uniform type. These tensors flow through a graph of operations, which are called ops. The graph of ops describes the computation that TensorFlow will perform. TensorFlow allows users to define their own custom ops, which enables them to express very complicated machine learning models. TensorFlow has a number of advantages over other machine learning frameworks. One of the main advantages is that it is designed to be scalable and efficient. TensorFlow can run on a single device, or it can scale up to run on multiple devices, such as GPUs or TPUs, which can greatly accelerate the training process. TensorFlow also has a number of tools and libraries that make it easy to develop machine learning models, including the TensorFlow API, which is a high-level interface for defining and training machine learning models. There are two main versions of TensorFlow, TensorFlow 1.x and TensorFlow 2.x. TensorFlow 1.x is the original version of TensorFlow, which is still widely used. TensorFlow 2.x is a major update to TensorFlow that focuses on simplicity and ease of use, and it is designed to be more intuitive and easier to use than TensorFlow 1.x. TensorFlow is used in a wide variety of applications, including natural language processing, image and video analysis, and speech recognition. It is also used in many industry and research settings, such as self-driving cars and healthcare. TensorFlow is designed to be flexible and extensible, so it can be used to build a wide variety of machine learning models. Here are some of the key features of TensorFlow. TensorFlow allows users to define custom ops, which enables them to express very complicated models. TensorFlow has a number of built-in ops and libraries that make it easy to develop machine learning models. These include functions for building and training neural networks, as well as tools for reading and pre-processing data. TensorFlow has a number of tools and libraries for deploying machine learning models in production. These include the TensorFlow Serving Library, which makes it easy to deploy trained models to a production environment, and the TensorFlow Lite library, which allows users to deploy machine learning models on mobile devices. TensorFlow has a large and active community of users and developers. There are many resources available for learning TensorFlow, including tutorials, documentation, and online courses. TensorFlow is designed to be scalable and efficient. It can run on a single device, or it can scale up to run on multiple devices, such as GPUs or TPUs. This makes it suitable for training very large and complex machine learning models. TensorFlow is a powerful tool for building machine learning models, and it can be particularly useful for natural language processing, NLP, tasks. Here are a few ways that you can use TensorFlow for NLP. Text classification. You can use TensorFlow to train a model to classify text into different categories. For example, you could build a model to classify news articles by topic, or classify customer reviews as positive or negative. Sequence labeling. You can use TensorFlow to build models that label the elements of a sequence, such as named entity recognition or part of speech tagging. Language translation. You can use TensorFlow to build machine translation models that can translate text from one language to another. Language modeling. You can use TensorFlow to build language models that predict the next word in a sentence or generate text that is similar to a given prompt. To use TensorFlow for NLP tasks, you will typically start by representing your text data as numerical tensors. There are several ways to do this, such as one-hot encoding. In one-hot encoding, you represent each word as a vector of all zeros, except for a 1 at the index corresponding to the word. Word embeddings. Word embeddings are dense, continuous vector representations of words. You can train word embeddings from scratch using a model such as Word2Vec, or you can use pre-trained embeddings such as Clove. Once you have represented your text data as numerical tensors, you can use TensorFlow to build and train machine learning models on that data. TensorFlow provides many tools and libraries that make it easy to build and train models for NLP tasks, such as the tf.keras.layers.embedding layer for training word embeddings and the tf.losses module for defining loss functions. Recurrent neural networks, RNNs, are a type of neural network that are particularly well suited to sequential data, such as text, audio, or time series data. In TensorFlow, you can implement RNNs using the tf.keras.layers.rnn layer, which provides a high-level API for defining RNNs. To use the tf.keras.layers.rnn layer, you will need to specify the type of RNN cell to use. TensorFlow provides several types of RNN cells, such as the tf.keras.layers.lsm cell, long short-term memory, and the tf.keras.layers.gru cell, gated recurrent unit. Here is an example of how to use the tf.keras.layers.rnn layer to build an LSTM-based RNN. Import TensorFlow as TF. Define the input data as a batch of sequences. Inputs equals tf.keras.input shape equals time steps, input underscore dim. Define the RNN layer. RNN equals tf.keras.layers.rnn tf.keras.layers.lsm cell units. Apply the RNN layer to the input data. Outputs equals RNN inputs. Define the model. Model equals tf.keras.model inputs equals inputs, outputs equals outputs. This code defines an RNN model with a single LSTM layer. The input data is a batch of sequences, where each sequence has time steps and input underscore dim features. The output of the RNN is the hidden state at the final time step. You can also stack multiple RNN layers or use a bidirectional RNN by using the tf.keras.layers.stacked cells and tf.keras.layers.bidirectional layers, respectively. For example, import TensorFlow as TF. Define the input data as a batch of sequences. Inputs equals tf.keras.input shape equals time steps, input underscore dim. Define the RNN layer. RNN equals tf.keras.layers.rnn tf.keras.layers.stacked cells tf.keras.layers.lsm cell units tf.keras.layers.lsm cell units. Return underscore sequences equals true.
Model architecture. Define the model architecture. Define a loss function and an optimizer loss underscore fn equals tf.losses.sparse categorical cross entropy from underscore logits equals true. Optimizer equals tf.optimizers.addm use the optimizer to minimize the loss. Train the model. For epoch in range num underscore epochs. For inputs, labels in dataset. This code defines a simple training loop that iterates over the training data and uses the optimizer to minimize the loss function. There are many additional features and options available for training and optimization in TensorFlow, such as learning rate schedules, regularization, and distributed training. TensorFlow can be configured to run on a GPU by using the TensorFlow GPU package, which includes GPU support for TensorFlow. To use TensorFlow with a GPU, you will need to install the following prerequisites: a compatible NVIDIA GPU with CUDA support, the NVIDIA CUDA library. Once you have installed these prerequisites, you can install the TensorFlow GPU package using pip. For example, To verify that TensorFlow is using the GPU, you can use the tf.test.is_pu_available function. Import TensorFlow as TF. This will return true if TensorFlow is able to use a GPU. To specify that a particular operation should be run on the GPU, you can use the tf.device context manager. For example, with tf.device/pu:0, all operations in this block will be placed on the GPU. Note that not all TensorFlow operations have GPU implementations, so you may need to fall back to the CPU for certain operations. Use TensorFlow serving. TensorFlow serving is a flexible, high-performance serving system for machine learning models, designed for production environments. It is a standalone server that can be easily deployed in a variety of environments, and it allows you to deploy new models without needing to take the server offline. Use a cloud-based serving platform. Cloud platforms such as Google Cloud AI Platform and Amazon SageMaker provide managed services for deploying and serving machine learning models. These platforms handle the infrastructure and scaling for you, so you can focus on developing and improving your models. Use a web application framework. If you want to build a web application that serves predictions from your TensorFlow model, you can use a web application framework such as Django or Flask to build the application and deploy it to a web server. Use a desktop application. If you want to build a desktop application that uses a tensor, apply the RNN. Apply the RNN layer to the input data. Define the model. This code defines an RNN model with two stacked LSTM layers, and the return_sequences parameter is set to true to return the hidden states at all time steps. You can then use the model to make predictions or to train it using an optimizer and a loss function. For example, define the input data as a batch of sequences. Inputs equals tf.keras.input shape equals timesteps, input_dim. In TensorFlow, a variable is a value that can be modified during the computation by TensorFlow. Variables are used to store and update parameters in a TensorFlow model. To create a variable in TensorFlow, you can use the tf.variable function, which takes an initial value and an optional trainable argument that specifies whether the variable should be included in the list of trainable variables. For example, copy code. Import TensorFlow as TF. Create a variable with an initial value of 0. V equals tf.variable 0, trainable equals true. Create a variable with an initial value of 1, 2, 3, 4. W equals tf.variable 1, 2, 3, 4, trainable equals true. You can update the value of a variable by using the assign method or one of the assignment operators, such as assign_add or assign_sub. For example,